Human hopes for modifying the weather know no bounds.
Yeah, this heading ought to be...
Another flight and a considerably different mission. A rendezvous with a hurricane. Project Storm Fury aims at eventually moderating the mightiest storms on Earth. They're feeling their way towards the central eye of the hurricane. Hurricane Ellen makes no headlines of disaster. She's steaming safely northwards through the Atlantic near Bermuda. Nobody's going to interfere with Ellen today. They just want to learn more about her. Their approach to the eye is recorded on the radar. The eye itself is calm, although among the towering clouds around it, the wind blows its strongest.
Say, John, the wind's picked up. We got 45 knots now. John's turned out to be a rainy thing up there. I haven't seen...
The hurricane feeds on the ocean and stirs it deeply, so elaborate but expendable thermometers drop into the sea. They signal the temperature at different depths as they sink. On this flight, they disclosed underwater waves in the wake of Hurricane Ellen. And there was particularly good news for the would-be tamer of hurricanes. A battery of instruments measured the ice and water in the air. They revealed, even in cold air, a surprising amount of liquid water. So much water, just asking, as it were, to be seeded and turned into ice. Yet, how could man influence a storm which releases energy at a rate equal to a hydrogen bomb every minute? The only chance would be to touch some critical point where a small change might have large consequences. From far and wide across the ocean, a hurricane or typhoon or cyclone, call it what you will, sucks in moist air. It throws it skywards in a wall of clouds around the eye. The water it carries now freezes, releasing energy that powers the storm. But American hurricane experts suspected that the storm's clouds would still contain a lot of water overdue for freezing. Seed the clouds here with silver iodide to encourage ice to form, and you might spread the zone of high winds and weaken them. In 1969, they seeded Hurricane Debbie, and it did seem to weaken, but that could have been just a coincidence. In any case, one man's shipwreck is another man's harvest. You have to be a good climber to be a radar engineer here. But at least the slope is even. They're climbing Mount Fuji in Japan, making for the summit 12,000 feet high. They have to supply and maintain the most elevated weather radar in the world. Built here despite the cold and fierce winds, it's very awkward to keep manned and serviced. The Japan Meteorological Agency never regretted the effort. Patterns of rainfall detected by this instrument are copied to all parts of Japan. But the special value of this lofty vantage point is that the radar can pick up, even 500 miles away, the signature of an approaching typhoon. It gives the Japanese ample warning of where danger threatens and so saves lives. Japan suffers some 4 typhoons a year, $400 million worth of damage. Yet, typhoons are welcome here because they bring 1/4 of all Japan's rainfall. So, Japanese strategy is clear. On the very rim of Fuji's volcanic crater, they have the keystone of their defenses against typhoons, the early warning radar. Be vigilant, then let the storms do their worst, and rejoice in the rain they bring. With this outlook, the Japanese want no one monkeying around with their typhoons to spoil their farming climate or else make the storms worse. So the Japanese are definitely not pleased that the United States and the Philippines are planning typhoon-busting experiments in the Pacific. The oceans, with storms raging over them and currents sweeping through them, play a decisive role in the world's weather. Like the air, the oceans are always on the move, but they're more difficult to study. It's only recently that ocean scientists found out that the oceans are full of tight little eddies, the watery equivalent of storms. Yet, what happens in the oceans has a major influence on the world's climate. Take the North Pacific in the 1960s. Then the surface water near Hawaii was rather cool. It was warm near the American coast. That guided the jet stream of the upper air along a path that brought warm weather to the western U.S., but left the eastern side of North America in the grip of cold winters. But that didn't last. In the 1970s, the sea temperature changed around. The jet stream has since tended to follow a different route, bringing cooler winters to California and warmer weather in the east. And urgent new research has begun into how the air and the sea affect each other in the Pacific Ocean north of Hawaii. The ocean is the second great fluid of the weather machine. The water's massive memory for heat and cold lasts much longer than the air's. Shallow patches of warm or cold water influence the weather in the air above. But the weather alters the water, and an American expedition is equipped to study the interplay. The good ship Flip gropes 300 feet into the subsurface waters by upending itself. The gear aboard her adjusts itself to life on the perpendicular. Well, most of the gear. Flip now monitors any changes at the various depths as she drifts in the North Pacific. And for a simpler and cheaper way of doing it, they're testing a giant buoy, 40 feet wide and proof against typhoons. It has a nylon tail with instruments on it reaching 1,600 feet down into the water. It automatically transmits news of the temperatures of the different layers. Everyone's after the water temperatures. This aircraft is armed with those expendable thermometers that sink into the ocean and signal the temperatures. Strange to say, it's only now that meteorologists and ocean scientists are really joining forces to ask basic questions about the oceans and the world's weather. How deep do the surface patches of warm or cool water go? How do currents and eddies affect them? How readily can a storm change the sea temperatures? This trial confirmed fears that the water's own weather is intricate. Comprehension of the oceans will come neither easily nor quickly, and the weather within them can be calamitous. The sea off western South America is usually bountiful. In 1971, Peru gathered the world's largest fish catch from water teeming with anchovies. Then the water changed. By 1973, the fishery was wiped out. The fishermen wait for the anchovies to return. They call visitations of this kind the Christ child, El Nino. They usually happen around Christmas. In normal times, a strong current flowing from the south eases away from the coast near Peru. In the gap, fertile water wells up from the depths of the ocean. If the current shifts inshore, it blocks off the fertile water and fishes starve. But part of the portrait of El Nino has to be drawn 9,000 miles away across the Pacific. In the atoll of Truk in the Caroline Islands, you're a long way from anything except the ocean. The tropical water hereabouts issues huge amounts of heat and moisture to the air. The ocean itself, the wet part of the weather machine, rivals the air in carrying heat around the globe. The fisheries of these islands neither aim so high nor crash to disaster like those of Peru far away. But they're linked by the flow of the ocean. Between Truk and the nearby equator, a great eastbound current of water runs against the prevailing trade winds. It carries warm water towards South America at up to 40 million tons a second, but sometimes it almost stops. When it surges strongly, the sea level falls a little here. That's the simplest way to detect the current's fickle behavior. Dave Miller's line is really electronics, but he takes care of the sea level here to oblige the folks who like to know such things. Someone will have to interpret this chart to find any small change in mean sea level. The ordinary tides have far more effect than that erratic current does in dropping or lifting the float that drives the recorder. The records are highly prized in a more accessible part of the Pacific. Here, too, in Honolulu, the trade winds blow. Sea level changes at various islands speak of surges in the currents. Klaus Wirtke of the University of Hawaii connects them with El Nino, which ruined the fishermen of Peru.
El Nino coincides with the surge of the currents in the mid-Pacific. The current transports vast amounts of water, of warm water, into the eastern Pacific Ocean, from where, for the months to come, it may affect the climate, for instance, of North America. There are a number of visitors around here, and I wonder whether these visitors realize that the weather at home in the months to come will be affected and created by the events here in the mid-Pacific. I think the surge in the current explains El Nino. Some of my colleagues disagree. They say weaker trade winds are causing El Nino. Now, my current runs precisely against the trade winds, so weaker winds will cause a stronger current. But what, in turn, makes the trade winds weaker? The ocean currents or the warm ocean surface water? You see, this is the kind of circular argument that we are getting into when we try to fit the pieces of the weather machine together all over the world.
The weather off the Pacific eventually arrives in California. And here to receive it is Jerome Namias of the Scripps Institution of Oceanography. For years, he's been studying the sea temperatures that are measured by merchant ships going about the world.
The ocean can affect the atmosphere over enormous distances and in fairly predictable ways. Take the weather today, for example. We're now on a beautiful day, bathers along the beaches, but actually we're sandwiched in between two storms. This is related to some very cold water, perhaps 600 miles off the coast, while farther to the west there's a warm pool of water, and the difference in temperature between these currents is causing these storms to move southward, affecting us right here. Now let me give you an example how the sea surface temperature patterns can influence all our lives.
In the Atlantic in 1972, patches of very cold water and warm water lay close together. The jet stream of the upper air became locked between them. It guided cold weather to Britain, which had a dismal summer, but it left the Russian grain lands with a great drought. World prices of grain shot up. Meanwhile, there was a trough of low pressure over the eastern United States. Hurricane Agnes was drawn into it, causing the worst floods in American history.
That's only one case, but we've all lived through spells of abnormal weather, including droughts, floods, hurricanes, and so on. And in order to forecast these things correctly, it'll be necessary to take into account the temperatures of the sea, not only locally, but over far reaches of the whole planet.
Long-range forecasting using nature's symptoms is gradually improving. Other problems surround the short-term predictions. Today's official forecast for this island in the Pacific was, you guessed it, sunny and dry. It's a freak rainstorm, too small and too short-lived to be predictable, and far beneath the notice of any computer. Yet these small events directly affect human life, and they also have hidden influences on the development of larger weather systems. So, small storms are not just awkward to predict in their own right, they also sap the power of the computers and undermine present attempts to predict the wider weather for a week or more ahead. The computers calculate at a limited number of points. They cope well with such a big depression, but not so well with small local storms. The small storms also slip undetected through the network of global observing stations, so the world's weathermen don't even know they exist. Not normally, anyway. Inexact starting information can send a computer forecast astray. At the U.S. National Center for Atmospheric Research, Cecil Leith wrestles with this element of chance.
The forecast is pretty much of a gamble. We have to learn how to hedge our bets. I'm using what is called the Monte Carlo method. Starting with the weather conditions on a particular day, we make a series of two-day forecasts differing by small amounts corresponding to our uncertainty in the initial conditions, and examine the development in each of these 8. We note, for example, that over China, a low moved toward the coast. In all of the 8 forecasts, we can be quite confident that this will happen. We also note another low near the Baltic, which remains stationary over this 2-day period, according to these 8 forecasts, and we can be confident of that. However, over the North American continent, the 8 forecasts showed quite different behavior, and in this case, we would have far less confidence in the validity of our 2-day forecast. Our best bet is the mean of the 8 forecasts, and in fact, as we compare that with what actually happened, we see reasonably good agreement for the lows in the Baltic and Asia, but some disagreement over North America. It is through a technique such as this that we hope that we'll be able to understand better how much confidence we can place in a forecast of, let's say, a week in advance.
Faster computers and better weather reports might cure half the errors in routine forecasts. But for a real breakthrough, more basic knowledge is needed. Okinawa has a doleful name. In 1945, this Japanese island shook with battle. In the end, the chief defender threw himself off this cliff. Today, only fishing boats litter the once disputed beaches, and Okinawa's the first theater in a quite different war. Each February, a bitter wind breaks out from China. As the islanders take in their sugar crop, they expect rain. The ocean is always warm in these parts, and it transforms the cold wind into a milder and wetter mass of air. The weathermen have made Okinawa their headquarters for the air mass transformation experiment. It's the first big operation in mankind's global atmospheric research program, aiming at better understanding of the processes of the weather. American satellite pictures assist them, and their research in turn will help forecasters all around the world. China influences the winter weather of the nearby ocean. The area is bathed by a strong warm current from the tropics. On convenient islands and specially stationed ships, the experimenters watch what happens when the cold, dry wind from China reacts with the sea 40 degrees warmer. It takes up moisture like a sponge. From the sea, invisible fingers of rising air carry off cargoes of moisture, fuel for the weather. The flows of warm air and moisture reveal themselves to towers festooned with sensors. It's all in aid of a quite small part of the weather machine, but one which affects the climate all around the world. Some of the instruments are very simple. This windmill measures the lift of the air. Others are ingenious, like the one that uses sound waves to feel the air moving through it in any direction. The effort is mainly Japanese, but weathermen from America and Australia have joined in. It seems fitting to take the measure of this Chinese wind with a kite. The instruments it carries measure the condition of the air at selected heights. The rising moisture gradually turns into clouds and rain. Meteorology's come a long way since the days of the old weather glass. A radar picks up potential raindrops beginning to descend a mile overhead. Some of the moisture that the sea surrendered to the air is already on its way back to it. The experimenters find that more than 4 times as much energy passes from ocean to atmosphere when the cold wind blows as does on a warm day. The facts and figures will let the world's computers put more accurate numbers to an atmosphere that boils and swirls whenever a warm sea is swept by a cold wind. The Japanese experiment off Okinawa will continue, but there'll also be a big study by the Indians and Russians of the monsoons of southern Asia. To fill in another gap, special weather buoys are going into the lonely Southern Ocean. And the Japanese, the Russians, the Europeans, and the Americans will also station satellites at agreed intervals. Together, they'll give continuous weather observations all around the world. The new powers that their satellites and computers give them have spurred the world's weathermen to a massive attack on the problems that still vex them. For another example, the Americans and the Russians are planning to see how Arctic ice affects the weather. They'll be using manned icebergs. It's all leading up to a global experiment around 1978. One aim of the Global Atmospheric Research Program, as it's called, is better weather forecasts for a week or more ahead. Now, there's increasing stress on a second objective, to understand changes of climate before they hit us any harder. Already in 1974, an extraordinary effort has gone into seeing more exactly how the clusters of clouds over the tropical oceans power the whole world's weather. The northern hemisphere, mapped by satellite, has a necklace of cloud clusters strung all around the equator and pumping vast energy into the weather machine. In 1974, the Americans stationed their newest weather satellite, called GOES, over the tropical Atlantic in time for the big party. In the late summer, the fashionable place for a weatherman to be was at Dakar in West Africa. A huge research armada assembled for the biggest international experiment in the history of science. The Atlantic Tropical Experiment of the Global Atmospheric Research Program, GATE for short. The Russians are here in force, and the Canadians have pulled their finest weather ship off station. Altogether, 40 ships from 10 nations are taking part. The world's nations are investing $300 million in the experiment. At Dakar Airport, Russian and French, British, and American research aircraft await their orders. Dakar is in Senegal, one of the African states hit by the recent drought. Near the coast, the people still prosper because there's fish to be had. But inland, those driven from their lands by lack of rain live as best they can. The governments concerned like to think the GATE experiment will help them judge better the prospects for their people. Under the UN flag at Dakar, the leading organizers of GATE include John Mason, head of Britain's Meteorological Office, and Joachim Kuttner from the USA. Pictures from the GOES satellite show the weather offshore.
So some of these aircraft missions then will be 10 or 12
Dr.
hours.
Kuttner's in command of the daily operations, and he has a welcome target. A cloud cluster is approaching the main experimental area, and it's to study how and why nature forms these ordinary yet vital clouds that researchers put to sea, bound for their appointed stations. Working to a strict timetable, the scattered fleet records the weather high overhead. We're aboard the Professor Zubov from Leningrad. Concentrated effort for a few months should reveal general rules on which the computers can rely ever after. Subtle mechanisms, both high in the air and deep in the ocean, may help to determine when cloud clusters will develop. Temperatures and saltiness at different depths are measured from the Canadian weather ship Quadra. A Christmas tree of instruments will register the upsurge of heat and moisture from the sea, while Quadra's powerful radar probes the clouds that form over the surrounding ocean. They'll signal the radar picture to the headquarters ashore. It's a valuable guide for the airborne missions into the weather that's unfolding over the tropical Atlantic. Such elaborate international efforts for studying the life of commonplace clouds marked mankind's impatience to know the weather machine better. Vast numbers of clouds, big and small, graze together on the warm ocean. From the satellite, a day in the life of one cloud cluster just off the coast of Africa. GATE, This experiment in the tropical Atlantic sums up the character and hopes of modern weather research. And because atmospheric waves going all around the world help to conjure up cloud clusters in the Atlantic, countries from East Africa around to South America had been supplying weather reports for GATE. As the satellites look down on the area, the computers calculate what the winds are doing. International collaboration is driven to the limit. The core of the experiment is here, a trap for cloud clusters made by 20 ships, Russian, British, Canadian, French, German, and American. They caught their cloud clusters. For instance, on the 30th of August, this one was pumping busily away over the core area, and the aircraft from Dakar went in to patrol among the stormy clouds. The experiment seeks general interactions between the cloud clusters and the global weather. Some cloud clusters turn into hurricanes. Here's one just forming that hit Louisiana, and here's another that's moving right into the weather of the North Atlantic. The main hope that inspires this very difficult research is that computers will predict the weather more reliably and further ahead. But meanwhile, to understand seasonal trends, the weathermen, as we saw, have to read all the available symptoms and take the temperature of the sea. In July of 1974, cold water on either side of North America conspired with the jet stream of the upper air to leave the American Corn Belt in drought. But by August, the route had changed. Letting cold polar air cause disastrous early frosts in Canada. Held south of its normal track by a cold Atlantic, the jet stream gave northwest Europe, too, a cold summer. And in early September, it guided unseasonable storms into Europe. On this particular day, the GATE experimenters observed another cloud cluster forming off Africa. It traveled west, and sweeping energy up from the Caribbean, it evolved into Hurricane Fifi, which flooded Honduras in one of the worst disasters of the year. In passing, Fifi robbed the world of a large crop of bananas, and the direct human suffering was terrible. While thousands drowned in water and mud, many others had narrow escapes. Every one of us is in the front line in mankind's endless war with bad weather. Fifi was only a skirmish. The weather machine is capable of far worse harm even than this. As it threatens the world with drought and cold, other ways of investigating the climate become important. The ice samples from the Greenland drillings informed us about weather of past centuries. We're going to see how pieces of living trees, the mud of the oceans, and the pollen of plants long since dead warn us about what our planet may have in store for us. And we'll hear of startling new discoveries about the risk of another ice age. But first we have a short intermission. I'll be back in a minute. This program is being made possible by a grant from Champion International Corporation.